All right, so we're continuing in our Algebra 1 skills review, and this is our third lesson in this review, and we're going to be solving inequalities. We'll be solving and graphing inequalities, just a review of that skill that you learned in Algebra 1. And then we're going to move on to a little more complicated, how do we do this solving and graphing of compound inequalities. So that's kind of the layout of today's lesson. But let's start with a real simple illustration. To solve this inequality, we're going to follow the same procedure as we did in the previous lesson when this said equals. So we're still going to try to get x by itself. We're going to follow PEMDAS in reverse. To undo subtraction, which is what I do first, I'm going to add. So I'm going to add 6 to both sides. So I always undo subtraction before I undo multiplication if I'm going to go in reverse order with PEMDAS. And now to undo multiplication, I can either divide or I can multiply by the reciprocal. So I'm just going to divide both sides of this inequality by 3. And here's one big difference. You can probably already see it. When we're solving equations, if there is a solution, it's just one number. When we're solving inequalities, if there is a solution, it's a range of numbers. In this case, it's any number we can pick that's less than 11. So the way we show that in picture form or graph form is with a number line. And this is the way I want you to do your graphs. It's nothing fancy really. I do want you to put 0. And then I want you to put the number that's part of your inequality in relation to 0 on the number line. So just, over here, in this case, over to the right a little bit. Now remember from Algebra 1, it says less than 11, which means 11 isn't part of the solution set. But all the numbers less than 11 are. So to make sure we don't include 11, we're going to put an open circle above 11. That's to indicate that 11 isn't part of the answer, but all of these numbers are. Now maybe in Algebra 1 you learned a little different way of doing it, and if you want to keep doing that, that's fine. Some people do this, and then they shade, and then they do the arrow. I'm okay with either one of those, whatever you like. But that is the two-part answer really. We'll solve the inequality, and then don't forget to graph your solution. All right? Let's move on to another example. Much like last night, if we have grouping symbols, operations within grouping symbols, we need to distribute in order to remove those parentheses. So 2 times 3n is 6n. 2 times 1 is 2. I'm going to combine like terms on the right side. I've got these two constants. 2 plus 22 is 24. Okay, and I've got two operations being performed on n. I've got multiplication and addition. So remember from last night, we do PEMDAS in reverse. We will undo addition first. So I'm going to subtract 24 from both sides. Now I undo multiplication either with division or multiplying by the inverse. Now, if you left this answer, if this were a homework problem and you left your answer like this, it's okay. But I'll give you a little suggestion in the event that you might be one of these people, and if you are, it's all right. In doing this for a long time, I see that there's some people that maybe they're a little bit confused on how the shading is supposed to go on the number line. So let me just offer this suggestion. Personally, I like to always have the variable on the left. In other words, I want to put n on the left side and -2 on the right. That's just me. But I'll show you why that's a good thing if graphing is a little bit confusing for you. Just be careful here, but Because do you see how the inequality is pointing at n in this case? When I turn these around, it still should be pointing at n. If it's not, then I've changed my answer. Does that make sense? Now, why is that a big deal? Well, it's a big deal for graphing because now, if I put the variable on the left and the number on the right, I can use this always to tell me which direction to shade. I know now that I'm going to be shading to the left. Just a thought, if graphing these causes you a little bit of trouble, and I've seen some people over the years that have a little difficulty. So here I put 0, and I put where I'm thinking -2 is in relation to 0. Now notice that it says less than or equal to. Well, that includes -2 as part of the solution. So for that reason, I need to put a solid circle above -2. It is going to be one of the possible answers. And once again, since my arrow is pointing to the left, that just tells me to shade to the left. But let me just repeat that. If you don't have the variable to the left of the number, then you can't just say, oh, I'm going to shade to the right. Obviously, if I shade to the right, I'm going to have the wrong answer. Does that make sense? So you can only trust yourself to know how to shade by looking at the inequality direction if you put variable on the left. So just a suggestion, be careful if you do switch it around, make sure that the inequality is still pointing, in this case, at the variable. Any questions about that? Everybody good? Okay. Let's try this one. Once again, I'm going to do the distributive property to remove grouping symbols. I'm just going to skip a step, I'm going to subtract 3x. I know we typically say kill the little one, but I'm just going to go ahead and subtract 3x from both sides. Now, the reason why I put this problem up here is because it reminds us when dealing with inequalities, there's a very important rule. And I wonder if you remember what that is. It's going to come into play with this problem. There's a rule involving inequalities that we did not have to worry about with equations. Anybody want to take a stab at it? Yeah?
Improper fractions?
No, they're okay. It has to do, I'll give you a hint. In order to solve for x, I'm going to have to divide by what? -5. That ring a bell? Dividing by a negative number. What does that force me to do with an inequality? Don't remember? Yeah, we got to change the direction. So just wanted to give you that reminder. If you end up dividing or multiplying by a negative number in solving for an inequality, then you're going to have to switch the direction of the inequality symbol. Very important that you remember that. Have you ever wondered why that is? Are you curious about stuff like that? Okay, let me give you a real simple illustration that if it sticks, it's so simple, but if it sticks and it helps, then it'll be worth it. I'm going to do a little number line, and this is something that you probably would have done in elementary school. I'm just going to make up a couple of numbers. Here's -8, and I'm going to say over here, this is 13. And in elementary school math, you may have done some exercises like this. Here's a box, and your teacher would have said, okay, what inequality would go in the box to make this true? Would you say less than or greater than?
Less than.
Less than. Everybody agree with that? Okay. Now, what if I divide all the way across this number line by -1. It's going to make this number become what? And this number becomes, is my inequality symbol still true? So dividing by -1 forced me to have to also change the inequality in order to remain true with the way the numbers are lined up. That make sense? Any questions? Yeah?
So you divide by -5, but it's a -15, so it would be +3?
Yeah. Thank you. Thank you so much. Sorry about that. Negative divided by negative is positive. Thanks. That was Jonah. Jonah Lane. Yeah, good catch. You have a question?
Is it, you said that like you have to flip it if you multiply or divide?
Or divide. Yeah, just those two. If you do either one of those things, it only applies to multiplication or division of a negative. If you multiply or divide by positive, nothing changes. Good question. Anyone else? Question? This is probably the most commonly made mistake on these problems, forgetting to change the inequality direction. Okay, now let's get to some what you might call weird problems. Maybe to you they're all weird, but these are exceptionally weird. And you'll probably notice it right off the bat. If I do the distributive property on the right side, I get this. Now my normal routine is to try to get x terms on one side only. So since this is positive, I'm going to subtract 2x from both sides. What does that give me? There are no more x's. 2x minus 2x is 0, so on the right side I'm going to get -3. 2x minus 2x again is 0. I'm sorry, the left side I'm going to get -3. The right side I'm going to get -10. Huh, interesting. The variable's gone. But what I need to ask myself is this. Is the inequality that is left over true? Is -3 greater than -10? Okay, so when this happens, when this unusual case happens, and it will on your homework, when the variable is gone, it cancels, and what is left is a true statement. Then you're going to go one step further, and you're going to put this as your answer. All real numbers. In other words, any real number you can think of will make this a true inequality statement. It doesn't matter what real number you pick. As long as you plug that same number in for both of the x's, you work this out, the left side is going to be greater than the right side. But that's only true, that is going to be the answer only if when the variable drops out and you're left with a true inequality statement. Okay? Well, let's take a look at another weird situation. So once again, I'm going to distribute. I'm going to try to get the x terms on the same side, but obviously the same thing is going to happen. If I subtract 7x from both sides at this point, the x terms are gone, and I'm left with an inequality statement, but is it true? Is 0 greater than or equal to 14? No. So now I need for you to be prepared. Well, what happens when the variables are canceled and you're left with a false statement? We can probably conclude if the true statement gave us an all real numbers solution, what do you think the false statement's going to give us? No solution. There isn't a number that you can pick, no matter what it is. If you choose any number in the real number system and you replace both of the x's with that number, it's not going to make this work. It will not make it true. I mean, you can test it if you like, but to save time, just take my word for it. Here's what I need you to do on the homework tonight. Don't just get to this point and stop and say, yeah, that's false. I need for you to go one more step and interpret that solution. In this case, we're going to say it's no solution. So the false inequality statement gives us no solution when the variables are canceled, and the true statement gives us all real numbers, no solutions. Okay, we're almost done. You guys are doing great. Let's talk about compounds. There's really two types. Compound means two inequalities that are together in a problem. And the way they're joined together, it's either, there's one type that will be joined together by the word and. And then there's another type we'll look at on the next slide, joined together by the word or. And they're pretty different. I want you to see how they're different in the way they're graphed. Well, really, we're just going to treat this as two problems, even though it's one problem joined together by the word and. Two different inequalities joined by the word and. So let's just go about solving each one of these separately. So Phoebe, help me out with this one. If I'm going to solve for x, what would I do first? Subtract 4 from both sides. Very good. And then Phoebe, what would be the next step? Divide by 3. And on this side of the word and, I've got a solution that says any number greater than or equal to -1 will work. Okay, so Brian, let's do this one. What's the first move?
Subtract 7.
Okay.
And then divide by 2.
-2?
Yes.
And that means I've got to do what to the inequality?
Switch this.
Switch it, very good. And I'm going to put the word and between them. So let's think about this. By using the word and, what we're saying is this. Our solutions are going to come from all the numbers that are -1 and bigger. That's what this says. But those numbers also, because it says and, not only must they be this, but those same numbers also have to be described in this way. So bigger than -1, including -1, but also less than 1 or 1. So give me a number, just shout out a number that would satisfy both of these. Give me a number that is both greater than -1 and it's also less than +1. 0. Okay, give me another. 1/2. Another one. 0.2, okay? Another one. -1/2. -3/4. +3/4. Do you see what we're describing? Can you kind of put it in a sentence, the numbers that we're calling off? How would you describe them? The numbers that are between. Good word. I want you to think of the word between when you see the word and in a inequality compound. And here's why. If there is a solution to an and compound, I always use my hands to illustrate what the graph looks like. The graph of an and compound always looks like this, if there's a solution. It's all the shaded numbers between two numbers. If there is a solution to and you do a graph of the solution, and it doesn't look like this, two endpoints with a shaded bar between them, you've done something wrong, because this is the way the graph always looks. Okay? So let's go ahead and do the graph. all the numbers in between 1 and -1 are solutions, and we're going to include 1 and -1 because they both say or equal to. So I'm going to put a solid dot above +1. I'm going to put a solid dot above -1, and I'm going to show between with this line segment connecting them. So any number we can come up with, as long as it falls in this area, will make both of these work, and that's a key. If I pick a number, it's got to make this one work, and by virtue of the fact that it says and, it also has to make this one work. It's got to make both. All right, so now that we're in Algebra 2, maybe you've seen this in Algebra 1. In Algebra 2, when you're writing the answer to an and compound that's not a no solution answer, I want you to write it like this. Are you ready? So let's put -1 on the left, +1 on the right, and the solution, this shaded area, is my solution for x. So I'm going to put x in the middle. It's pretty easy. If you're looking at the graph, then writing this solution is really pretty simple. X is represented by the shade, low number, high number. And then we're going to put less than in between, like this. So that might be something that you have not seen and you've maybe not been asked to do in the past. But instead of writing your and compound solutions using the word and, I'm going to ask you to write them like this. And if I were reading this in words, it says my solution falls between -1 and +1. So let me give you a heads up. A lot of people get a little confused about writing this, and they'll do something like this. Okay? First of all, if you write these in order from lowest to highest, which you should, these should always point in the same direction, and they always point less. Think about this. The way I have this written right now, I'm saying that -1 is greater than 1. Well, that's not true. So just make it easy on yourself. Write them from lowest to high. Always put the variable between, and these always point left every single time. And it might take a little getting used to, but we'll keep working on it. And this will help you for math classes down the road as well. So this is the and compound. It always, if there's a solution, it always looks like this. So now let's look at some or compounds. We're almost done. Hang in there. How is or different? Well, let me run through solving these first. I'm solving the left inequality. I get x is less than 4. That's a possible solution set. But this says you've got another one. You could also use all the numbers described in this way. And means that it would have to be both. And means I could only use numbers that are less than 4 and at the same time greater than 5. Can you give me a number that's less than 4 and greater than 5? Don't think so. There aren't any numbers that are both less than 4 and at the same time greater than 5. So if this were an and statement, it would be no solution. But since it's or, it doesn't have to be both. I can use either one. Either one of these sets of numbers will work. And so here's my graph. It's going to be 2 lines showing all the numbers less than 4, but not including 4. I'm going to use an open circle, shade to the left. Those are okay to use. But I can also, I'll be correct if I use all of these numbers. I'm not going to include 5 because it doesn't say or equal to, so I've got an open circle above 5 shading to the right. So unlike and again always looks like this. It's always shaded between 2 numbers, or it could take one of 3 forms. Well, here's one of them. 2 lines that branch out going in opposite directions. Here's another form that OR could take when graphed. Solving the left inequality, I get x is greater than or equal to 1. The right inequality, x is less than 6. Well, let's put both of those lines on the same graph. Here is all the numbers from 1 and then going to the right. We're getting bigger. Here are all the numbers starting at 6 and going to the left. Well, if I told you to get the solution to this, you can choose any number in the following groups, and you'd be okay. You'd be right. You can pick any number from 1 to positive infinity, any number you want, or if you want to, you can pick from this set of numbers from 6 all the way to negative infinity. And any of those numbers from either group would be fine. So I've just described what? If I said you can take the numbers from 1 to positive infinity, those are yours to use, any number you want. And, or if you want to, you can use this set of numbers from 6 to negative infinity. What have I just described? Any number. This represents every single number there is. And so when you have this overlapping lines that go in opposite direction, one's going to positive infinity, one's going to negative, then all we're going to say is, well, that's all real numbers. Any number that exists will make either one of those true. So for OR, you can have two lines going in opposite directions, and that represents your solution. You can have overlapping lines going positive, negative, infinity, which is really another way of saying any number. Well, let's take the other scenario. I've already solved these for you, so let's graph them. I'll give you a chance to go ahead and just sketch the graph of all the numbers greater than negative 4, and then do a separate line to show all the numbers from negative 8 going positive. Looks like most of you did a great job. I'll just sketch this graph. And we'll show greater than negative 4 like this, open circle, shade to the right. And I'm just going to say negative 8 is here. Closed circle, shade to the right. Do you notice something about this? Isn't this kind of redundant? Could we really just use one of these and it would include the other one? Yeah, what if we just said all the numbers bigger than negative 8, including negative 8? Would that capture these as well? Wouldn't it? So why say both of these? Why not just say the one that will really take in the other? And that's a better way, a more succinct way of showing the solution. So, I mean, this is not terrible, but sometimes in multiple choice questions on quizzes or tests, you're only given one option, and you want to make sure you're able to pick the correct option. Does that make sense? Okay. Any questions so far? All right. I've given you the slide that contains the problems, and you access the document the same way. You go to RenWeb in the lesson plan area.